What about the ground? What temperature is the ground in winter? 10 degrees, 8 degrees?
Minus 10, I think.
Yeah, minus 10 when you get to the surface, yeah?
Okay.
But down, a couple of metres down, then you're already into a plus 8 or 10 degrees. That's 30 degrees more than it is outside in Denmark in winter when it's minus 20 here. So there you've got an instant way of source of energy, just the ground underneath the building or underneath the first metre. And what I've tried to sketch here is one way of using that. You can see here in the building laws, you've got a need for ventilation. Does anyone know what the need for ventilation is in the building regs? Can you remember that? 0.3 litres per second for every heated square metre of house. This is a lot. That means you're actually changing the air twice an hour in a building of 2.4 metres high. How do we do that so that we're not, when it's minus 20 outside, you're opening up the windows and the doors to change the air and you're getting rid of your plus 20 degrees of heat? One of the ways that we can do it is by putting in a ventilation system and using the heat from the ground. Here you can have the air intake going down underneath the ground, minus 20 when it starts, the ground's got plus 10, so by the time it gets to your aggregator, I heard some of you saying, what's an aggregator? An aggregator is where you've got a heat exchanger for your ventilation.
Where you can place it?
It's placed many places. In this sketch I've shown it in the cellar, or I've actually shown it in the ground floor. It could be in the cellar. It could be, if you look at IKEA, they put these ventilators up on the roof.
If you have flat roof.
To save space. So you guys can put this aggregator many different places.
In the basement?
In the basement's a very good place for your technical room and for your aggregator. But if you look at it, maybe it's a time just to give an overview as to the sketch here, because you have to provide by the laws 0.3 litres per second. Yeah? That means that into these rooms where you're living, you've got to provide this air. And we don't want to provide it with minus 20. So what we do is we take this cold, fresh air, heat it up a little bit under the ground. This is not necessary, but it's a good idea. It's not everyone that does this. You could just take your air intake in, take it down your shaft, and into your aggregator, but then it's minus 20. Here I'm saying the effect of the minus 20 and the plus 10 could give a temperature at the aggregator of 0 degrees. Now we want to blow in, we don't want to blow in at 0 degrees, the ventilation air. We want to blow it in at something like 20, 25 degrees. There's a rule of thumb when you do ventilation design that you want the air to be 6 degrees warmer than the room temperature, so you don't feel the effect of like a cold air blowing on you. So you want to get aiming at maybe, say, plus or 25 degrees. But you've only got 0 degrees, even though you've got the heating from the ground. So what you're actually doing with this aggregator is you're taking the dirty, wet air, for example, from the bathroom, or from the other rooms, like your utility room where you're generating heat, or maybe even just your kitchen, and you're putting that air into your aggregator. So you've got a heat exchanger that's mixing the two together, and then, once it's mixed, then it can be put into the rooms that you're needing the fresh air. Now this mixing in a house, it goes through a heat exchanger, and that heat exchanger, if I sketch it for you guys, you get air coming in, and this heat exchanger is split up into all different panels. So the air gets circulated through these different panels. So that would be your minus 20. And then what happens is you're getting the dirty air that's coming in at maybe plus 25 into this heat exchanger in the aggregate. That goes the opposite way in this heat exchanger. And the result coming out of that would be the combination of, if it wouldn't be minus 20, if you used the ground heating, it would be 0. Plus the 20, maybe you end up with plus 10 degrees, maybe plus 15 degrees. Still a little bit cold to be blown in, but at least now you've taken the need from the building regulations, and instead of just opening a window or door, you've found a really economical way by actually just using the energy that's existing in the building, the heat in the building, but it's dirty air. So when you're mixing them together in a house, they're not actually coming in contact with each other because you're not wanting to pollute the clean, fresh air. You got it? And this is called a heat exchanger. In larger buildings, they actually do mix them. Just like a big tumble dryer where the airs get mixed together. And then you can reduce the content of CO2 in the air just by diluting it. That is what we call mechanical ventilation. Natural ventilation is the opposite. That's when you just open the windows or the doors and allow the natural air to come in. But you can also generate a natural ventilation. If you think of a chimney, if we had a chimney running through this building, or like your shaft, it generates an uplift, doesn't it? A chimney, that's its idea. So you can create an uplift, which is creating a negative pressure in the house. So the negative pressure in the house means that it draws air in. So you can create a natural ventilation with a chimney effect. So that's the sort of stuff that we're going to be talking about, that you're going to be learning. When we calculate the energy, Meta is going to show you a program called BE15, because the energy here, it's an extreme complex calculation. You're thinking about the heat that's coming through your buildings, like your walls and through the roof. You've got U values for all of these. And then you've got all these different areas that you've got to calculate. So you end up with a heat loss coming through all of these different parts. But there's many more things. What about the effect of these passive heat? So all of these things, like your U values, and your areas, and your passive heat, and your sun cells, where's the sun cells? They all go into a big program called BE15 and generate an answer. So the answer from the program here is going to be getting measured in watts per square meter of the building, Kelvin, and kilowatt hours. And to make things more interesting, all of these calculations that you learn, you can then combine it to the laws for energy. So you get a result here for your building based on all your U values, and then you compare it to the building regs and see if your overall building, with all of these things, with your sun cells and your passive heating and your U values, if it meets the regulations. So that's a big part of this second semester. So the skills that you're going to learn is how to actually work with all this knowledge. All these things that we're talking about, these are the skills that you're going to be working with. What you're going to produce, for example, is going to be drawings showing all these installations. So what I'm showing here in a sort of sketch or a 3D, you're going to have, and be putting it onto your plans. And at the end of this presentation, you get an overview as to the different types of drawings and scales of the drawings that you're going to have to produce. For example, prepare drawings for authorities for DD1, showing drain pipes, sewer pipes and rainwater. So these what I've shown on the drawings here, for example, for the toilet or your rainwater in red, where it comes down a gutter, down a downpipe, into an inspection chamber, and then out to the connection point. you've got to show now onto your plans. But you've also got to show some sort of section like this as to where you're putting all these pipes. Because what happens here, guys, remember yesterday we were talking about this light deck and we were talking about posy joists. The black lines here, they're showing where the joists would be. But how do you get the pipes from here? Where are they going in your construction? Before they get to the shaft? Before they come down the shaft and come out?
Through
So
the
there's a need for you guys to understand in your design, where are we putting the pipes? And that's why these posy joists, remember the ones with the holes, are ideal here, that the pipes can go across, parallel to the joist, go through the holes and get into the shaft. But what do you do here with the shaft? If you think that you've got a shaft that's coming all the way up and down through here, the shaft's going to probably be bigger than the centre to centre of your joists. So you're going to have to leave an opening here in your drawings and your design for the shaft. And also here with the heavy deck, you can't lay a big heavy deck section and also have a shaft coming up through it. So what you do is you're going to have a design, something then to support the shaft underneath here. Where is this heavy deck going to sit when it comes here? You see that? So these drawings that you're going to be doing, both for the drainage, they've got to be related also to my statics lessons, so that these different subjects go up in one.
So actually the thing down on the part of concrete on the
Yeah.
heavy deck,
Yeah.
you need to have like a hole there,
You've got to have a hole
but
there, yeah.
to
And
be
here.
but down there must be in the connection with the foundation as well, because for the stability and for the loads.
Yeah, the loads of this is, you're coming with, just think if my telephone here was a big heavy deck section and you've got a hole coming up through here for all these services. What's this end of this going to sit on here if there's a hole there? Maybe it's got to sit on the shaft itself, but that means that the shaft then's got to be able to take the loads.
So it's not only it's going until down in the basement or what you
Yeah, it's
have
coming-
there
Because
in
you've got to have
foundation.
loads of services down in the basement that's going to come up this this shaft. And that will bring me to remember, later on I'll give you a presentation about the fire. What do we do with the fire? Because you know in the fire regs you've got to isolate the fire from the basement, from the rest of the building. And what we actually do is what I suggest is that you make a fire sealing here, and you seal all the pipes where they go through the fire stop here. You make a fire stop at that point, so you seal the basement from the rest of the building. So you're isolating the shaft from the basement. The same way as you isolate the stairwell from the basement to the rest of the building in fire. Okay, we'll make a stop there because I think that's a good introduction. And
Stop there.
yeah, then we can start up again with the next phase of the lesson. Yeah.